Hi, my name's Tom George, and welcome to Physics 2212, Lab 3, Magnetic Field of a Bar Magnet. So, the purpose of this lab is to understand how the magnetic field changes as it relates to distance, orientation, and other factors. Additionally, we're going to compare the theoretical and experimental values for the magnetic field. So, the fundamental physics principles that we're using are magnetism. Basically, things with moving charges create magnetic fields. And then the Biot-Savart law, which is related to that. And then derivations of that law are going to be used to model the magnetic field at different points. And GlowScript is the main model to produce a visual for the magnetic field at different points. And so our preview, we see that the magnetic field of a bar magnet is twice as big on axis than its perpendicular, and the magnetic field is inversely related to its distance squared. So some of the physics ideas, magnetic fields can be created by anything with a moving charge. So this can come in a lot of different forms. It can come in current-carrying wires, or it can come in the case of inherently magnetic materials. So the Biot-Savart law is a way to describe magnetic fields, and you can see it on the equation there to the right. It's important to know that the equation uses a cross product, meaning that the direction of the magnetic field is always perpendicular to the current, or to whatever charge is moving. So magnetic fields in bar magnets, like shown below there, and solenoids can be described using a magnetic moment, similar to how electric fields could be described using a dipole moment. This magnetic moment in bar magnets points from the south pole to the north pole, and we use the equation there over to the right. So for our lab setup, our initial conditions, we'll see it in the next slide, but we oriented the phone so that the net magnetic field was only in the y and z directions and only caused by the Earth. And then the system is the phone and the magnetometer, and the surroundings are the Earth and the bar magnet. And the assumption is that outside of the Earth and the bar magnet, there are no other sources of magnetic fields. So how did our lab work? Basically, we aligned our phones so that they were in the same direction as Earth's north-south axis, meaning that there was no x component to the magnetic field. This would allow us to independently calculate the magnetic field due to the bar magnet. And basically, that's what we did. At different distances, we measured the electric field due to the bar magnet. We did this on axis for a few different versions, and then we also did it, as you can see in that bottom left picture, at a 45-degree angle to the axis. So we can see in this first chart, we measure the magnetic field, or the radius required to achieve a magnetic field of 20 microteslas, 70, 120, 170, and 220 microteslas. This chart to the right shows the Ln of the magnetic field versus the Ln of the distance. We'll see why I do this in the next slide. And then the final chart shows the off-axis magnetic field, so 45 degrees to the bar magnet. So we know that the magnetic field is equal to this constant k r to the n. And if we Ln both sides of this equation, we get Ln of bx equal to Ln of k plus n times Ln of r. This is very similar to y equals mx plus b. And so using this, we can use the graph to determine that k is equal to 1.1 times 10 to the negative 6, and that n is equal to negative 2.654. We know that the magnetic field is also equal to this when it's on axis and very far away. And if we set these two equations equal to each other, and we calculate it out, we get a magnetic moment equal to 5.89. And then, so for our coding, the first thing we did is we created the magnet, and we gave it that magnetic moment calculated in the previous slide. And then we created a function that gives the magnetic field at any point in space. After that, we created lots of observation locations to indicate the magnetic field at those locations. And then we created the off-axis one, like we did in real life. And so the results of that are shown in this diagram over to the right. We know that the magnetic field perpendicular to the magnetic moment is half the magnitude, and it is of the opposite direction to the magnetic field on the axis. Additionally, we can see that the magnetic field at 45 degrees has a greater y component than it has an x component. So some differences, the magnetic field in the code was this, and the magnetic field in the experiment was this. Both methods showed that the y component was greater than the x component by a factor of about 2.5, but the total magnetic field of the experiment was far less than the magnetic field shown by the code. So what are some sources of error that could have caused this? Well, there are likely other external magnetic fields than just the Earth and the magnet, which could distort the calculations. It's also possible that the Earth's magnetic field was not fully accounted for, that the app was not calculating it correctly, or perhaps some human error. If we hadn't oriented our experiment to compensate for the magnetic north, our results would have been very inaccurate, since we're using the x component of the magnetic field to be equal to the magnetic field from the magnet. Not zeroing this out would lead to a very different value. If we were to stick two identical magnets together, what would happen? Well, our experiments would differ by a factor of 2, assuming that the magnets were much smaller than the distance between them and the observation location. This is because of superposition. So, our conclusion.